Hi everyone, so we are going to continue with adding and subtracting radicals today, and we are going to add and subtract unlike radicals. So yesterday we talked about radicals that were like radicals, meaning they had the same radical and therefore you were able to add them. So 2 radical 3 plus 5 radical 3 is equal to 7 radical 3. So because these are the same, we can add the outside. 2 plus 5 was 7, and the radical stays the same. Same thing with variables. Because these radicals are the same, 3 radical x plus 7 radical x, we can combine them just like you combine like terms. 3 plus 7 is 10, and the radical stays the same. And then we had an example of when we couldn't add them. So 2 radical y minus 5 radical yz. Yes, they both have y's, but they look different. This is a y and this is a yz. So we cannot combine them. So your final answer would have just been the same thing, 2 radical y minus 5 radical yz. So we're going to move on to what happens when they're not alike, but in some cases we're really still able to combine these. So I want you to make sure that you're copying these notes down, and I will give you a second to do that. So today, you can pause this if you need to. So today we are going to add and subtract unlike radicals. And sometimes radicals do not look alike until they are simplified. Simplified means exactly what you've been doing before we started adding, so last week and the week before. When you simplify a radical, you just put it into simplest form. So you're using your powers table, you're using your calculator, and I stressed how important that was because we cannot do today's lesson if we do not know how to simplify radicals. And we're going to go a lot slower than we would in class, so take your time with this, and if you need to pause, please feel free. So go ahead and keep copying this down. We are going to make a rule for adding and subtracting radicals, and the rule is very simple. You must have all your radicals simplified before you add or subtract. So simplify all radicals before adding and subtracting. Just like fractions though, some radicals are already in simplest form, so it's up to you to decide whether or not the radical is simplified, but we're definitely going to do examples. Okay, so let's start with some pretty basic examples. Example 1 would be the square root of 45 minus the square root of 20. So when you look at this, you notice that they're not the same radicals. However, these radicals could be simplified by themselves. So I could actually simplify the square root of 45, and I want to simplify it. You cannot add or subtract unless everything is simplified. That's why I'm using this rule up here. Simplify all radicals before you add or subtract. So I'm not going to worry about subtracting if I know I have radicals that need to be simplified. So the square root of 45, there's many numbers that multiply to 45, but I'm specifically going to use 9 and 5. And I'm going to simplify. I'm using these because 9 is the biggest perfect square that goes into 45. And the square root of 9 is 3, so I bring down the square root of 5. So square root of 45 simplifies to 3 radical 5. I cannot simplify that anymore, so I'm going to move on to my next radical, which is the square root of 20. And for the square root of 20, think about what you'd want to use to simplify the square root of 20. Think about all the numbers that multiply to 20. So I'm thinking 1 and 20, 2 and 10, 4 and 5. Decide which pair you want to use. Remember, you want to use the biggest perfect square that goes into 20. So what you should have picked was 4 and 5. And just a little hint, to know if you actually picked the biggest perfect square, and I've discussed this in other notes, but I just want to remind you because simplifying is so important, you just have to do it all the time in this unit. I'm choosing 4 and 5 because I'm saying to myself, well, 4 is the biggest perfect square that goes into 20. And the way I could be sure is if the other number, which is the square root of 5, if that can't be simplified, then I know I picked the best pair for 20. So the square root of 5 can't be simplified. There's no number that goes into 5 that's a perfect square, other than 1, but 1 doesn't count because 1 goes into everything. So I did pick the right one, and I'm going to simplify the square root of 4 and get 2, and then bring down my square root of 5. So the square root of 45 turned into 3 radical 5, and the square root of 20 turned into 2 radical 5. Now that they're both simplified, now I can add or subtract, and in this case we're subtracting. So if you notice, once I did simplify them, now all of a sudden they are actually like radicals. They both have radical 5. So now I am able to subtract. So since they're like radicals, I can just subtract the outside. 3 minus 2 is 1, and I bring down the radical 5 with it. Now we all know 1 can be invisible, so 1 radical 5 or radical 5 works. It doesn't matter. Delta Math will accept either one. This is a review of last year. We're going to stick with square roots. We'll move on to different roots beyond cube roots next week. I just want to take it slow and us get used to the actual steps, because the steps don't change. Whether these were square roots or cube roots, simplifying them changes, but not subtracting them. All right, example 2. Nine radical 75 plus 2 radical 50. Okay, I'm going to simplify these first. For 75, I'm going to use 25 and 3. I'm going to bring down the 9. It's not part of me reducing the 75, but I'm going to need it in a second. There's no radical sign over it. I'm not simplifying it. I just don't want to forget it. So the square root of 25 turns into a 5, and I bring down the radical 3. So the square root of 75 turns into 5 radical 3, but there is a 9 on the outside, which means whatever this answer has, I have to multiply that 9. And 9 times 5 is 45, so 45 radical 3. So I just simplified 9 radical 75. I simplified the square root of 75 into 5 radical 3, and since 9 was being multiplied by the square root of 75, 9 is now going to be multiplied by whatever I simplify the square root of 75 to. And that's why I ended up multiplying. Then I have 2 radical 50. For radical 50, I'm going to use 25 and 2. And square root of 25 is 5. I'm going to bring down the radical 2. And I almost forgot I have this 2 here, so I have to bring that down in front of the 5. I'm going to multiply my outsides. 2 times 5 is 10. So I get 10 radical 2. So now that they're each simplified, I can attempt to add them. So 9 radical 75 turned into 45 radical 3. I can't simplify this anymore because nothing can go into radical 3, a 3 that's a perfect square. And I simplified 2 radical 50 into 10 radical 2. So now that they're simplified, I could attempt to add and subtract. But what do you notice about this addition problem? If you said that they're not like radicals, you're right. I cannot add them, or I cannot combine them, because this is a radical 3 and this is a radical 2. So this is fully simplified. I just can't combine. So I'm done at this point, because radical 3 and radical 2 are not like radicals. This does not mean that all this work was pointless. We always have to be in simplest form. Your work always must be simplified. Always must, yes. So this is correct. If you were to actually put this into, let's say, Delta Math, you'd get it wrong because it wasn't simplified. You would have to be in simplest form. So in this case, we had to simplify. We went to go add, but we did not have like radicals. So this is our final answer in simplest form. 45 radical 3 plus 10 radical 2. Okay, let's do some cube roots. Now, I did say you'd probably get better as you went along, and most of you, I think, have already seen that, but I do have my power tables out at all times in front of me. Remember I said last time when you did this a couple weeks ago that your copy doesn't have this blacked out, you should have numbers there because you're going to be using those. I just have an old copy, so but let's actually work on, let's do a cube root example because these are square roots, and we'll work more with like more roots next week as well. Like I said, I want to go slow with you guys on this since you are working from home. So let's do example 3. Let's try the cube root 3 times the cube root of 54 plus, let's see, 5 times the cube root of 135. Okay. So these are cube roots. Remember, you're looking for perfect cubes that go into these. They're obviously not the same radical. This is the cube root of 54. This is the cube root of 135. So I can't add them quite yet. I'm going to have to simplify. Okay. So with the cube root of 54, I'm trying to find the biggest perfect cube that goes into 54. So I'm going to use my calculator and divide. And here's a little review. If I'm trying to find the biggest number that goes into 54, where's my C? Okay. Well, I'm looking for perfect cubes, and I'm looking to simplify the cube root of 54. Well, here's my x cubed column. 54 is not in here. 64 is too big, so I'm going to start by saying, okay, I'm going to divide 54 divided by the biggest number that could possibly go into 54 in this list is 27. There you go. 27 and 2 is what I'm going to use. I didn't get a decimal, so I'm okay. I can use 27 and 2 because 27 is a perfect cube. So the cube root of 54 turns into the cube root of 27 times the cube root of 2. The cube root of 27 is 3. My powers table tells me that. So the cube root of 54 simplifies to 3 times the cube root of 2. Okay, that's great, but there's a 3 here, so I need to bring that down. And it gets multiplied, because numbers on the outside get multiplied. 3 times 3 is 9. So the 3 times the cube root of 54 becomes 9 times the cube root of 2. If you notice, I didn't put the 2 for the square root, but I put the 3 for the cube root. As we talked about before, if it's a square root, you don't need to put the 2 there. It could be invisible, but if it's not a 2, you actually have to put the number there. And notice that it doesn't look like an exponent by the 9. It actually is in the right place. You want to make sure that you're spreading out your work. Okay, 5 times the cube root of 135. Here's my x cubed column. 135 is not here, so I'm going to find the biggest number that can go into 135. 216 is obviously too big because it's bigger than 135, so I'm going to try 125. I'm going to try dividing. Oops. Okay, I tried dividing. It did not work. So 125 didn't work. I'm going to move my way up to 64. 135 divided by 64 doesn't work. It's a decimal. I'm going to move up 27. There we go. 27 and 5. I got a whole number. So I'm going to use 27 and 5. The cube root of 27 is 3, and I bring down the cube root of 5. I also have to remember that there's a 5 right there. So 5 times the cube root of 135 turns into 15 times the cube root of 5. Now I can try to add them, but if you notice, they are not the same. This is a cube root of 2. This is a cube root of 5. So I can't combine these, so I'm done. But I am simplified. Okay, we're going to do one more example, And this is actually a couple more examples because I want to use variables. But okay, so we're going to take 2 times the cube root of 192 plus 7 times the cube root of 24. And we're going to attempt to simplify these because I can't add them. They are not the same radical. One's a cube root of 192 and one's 24. So I'm looking at my powers table. I'm looking to see what the biggest perfect square that goes into 192 is. So I want you to tell me, what is the biggest perfect square that goes into 192? Your answer needs to be a number in the x cubed list. Go ahead and try it. Okay. If you did this right, cube root of 192, the biggest perfect cube that goes into 192 is 64. That should have been your answer. So because the cube root of 64 times the cube root of 3 is 64 times 3 is 192, and 64 is the biggest perfect cube. And that's why your answer should have been 64. And the cube root of 64, so what's interesting about 64, it's a perfect square, but it is also a perfect cube. So be careful. The cube root of 64, if you look at your powers table, get some of you dizzy looking at this. The x cubed column, 64 is in it, and the cube root of 64 is 4. If I asked you for the square root of 64, you'd look in the square root column, and that's all the way down here, and that's 8. So be careful, you're using this 64 because we're dealing with perfect cubes. So the cube root of 64 is 4, and I bring down the cube root of 3. And let's not forget this 2. I'm going to bring that down as well. 2 times 4 is 8. So I just simplified this whole thing to 8 times the cube root of 3. And now we're going to do the same thing with this 24 here. And I want you to tell me again, what is the biggest perfect cube that goes into 24? Get your powers table out, get your calculator out, start doing guess and check, and tell me what goes into 24 that is a perfect cube. If you did it correctly, your answer should have been 8. Because 8 is a perfect cube, and 8 times 3 is 24. I can tell just by looking at this that I picked the biggest number because I know 3 can't be simplified. So 8 times 3 is 24. 8 is the biggest perfect cube that goes into 24, and now I can simplify. The cube root of 8 is 2. I bring down my cube root of 3. I also have to bring down my 7. I'm going to multiply and get 14 times the cube root of 3. There's a plus sign here. Okay, now we are ready to add. And what's great about this is they are the same radical. They are both cube roots of 3s and only that. So because they are cube root of 3, I can actually add the outside. So 8 plus 14 is 22, and I'm just going to bring down the cube root of 3. And there you go. We have added here and subtracted square roots and cube roots.